Hey students, are you ready to learn?
In 3, 2, 1.
Welcome to my channel.
We are done talking about groups, abelian group, and alternating group. Let's now proceed to the introduction of ring and field. Let's define first what is ring. A ring is a set of R with two binary operations, which are the addition and multiplication. It looks like this. In ring, we also have three properties that we need to satisfy. First, the R under addition is a commutative group or abelian group. That is the first one. Second is that multiplication is associative. And the other one and the last one is the distributive laws hold in R, wherein A plus B times C is equal to A plus B times C is equal to A times C plus plus times B times C. And A times B plus C is equal to A times B plus A times C. So let's have an example. Example 1 is Z with usual addition and multiplication. First, we need to see if Z is an abelian group. If you can still remember our example in our previous lesson in groups and abelian group, we have an example about integers. Thus, integer is a what? Correct. Integer is an abelian group. So, our first property is satisfied. Satisfied. It is an abelian group. For our next property, we have here that under multiplication, it is associative. So let's just have three elements from integer. We will get for our A, let's have a negative number, -2. Our B, we have 1. Our C, we have 5. So, let's try if it is associative. Since it is abelian, thus it is associative. But let's just see when it is associative. So we have -2 times 1 times 5 is equal to -2 times 1 times 5. So is it associative? -2 times 1 times 5 times 5 is equal to -2 times 1 is -2. So we have -2 times 5. We have -10. And -2 times 5 is -10. Therefore, it is associative. It is associative. For our last properties to say that Z is a ring, we need to satisfy the last property, which is the distributive laws hold in R. So let's have here let's just substitute the formula here. So A plus B times C, so we have -2 plus B1 times C 5. Is it equal to this? Our A is -2 times our C is 5 plus B is 1 times C is 5. So we have -2 plus 1 is -1 times 5. -2 times 5 is -10 plus 1 times 5 is 5. -1 times 5 is -5. -10 plus 5 is -5. Since it holds in distributive law, therefore, Z with usual addition and multiplication it is a ring. It is a ring. That's how to check if the given are ring or not. Since we are done with ring, let's now proceed to field. Ring and field, they are just connected. So field also have a properties that need to satisfy. In field, we have an additional properties which is field should have an multiplicative inverse, and additive inverse. If they do not have these two properties and it does not satisfy, then it is not a field. Since we have here an example in ring, which is D with usual addition and multiplication, it is indeed a ring. But let's test if it is also a field. So let's see if Z has a multiplicative inverse and additive inverse under multiplication. So we have here the ABC. So let's check if there exists a inverse for the integer. So let's have -2. Wait, let's erase. So let's have -2. -2 times any number, it should be equal to 1. So what number should we add to -2 so that we can get 1? 0. -2 times 0 is 0. So therefore, it is not 0. Let's try again. 1. -2 times 1 is -2. -2 is not 1. Therefore, 1 is not the inverse for multiplication. Since we cannot find it, let's proceed to additive inverse. So -2 plus any number, it should be equal to 0. What number should we add to -2 so that we can get 0? 1. -2 plus 1 is -1. 1 is not 0. Let's try again. 2. -2 plus 2 is equal to 0. So, 2 is the inverse of -2 under addition. So, since we are already get the additive inverse for -2, let's proceed to multiplicative inverse. Have you ever think any number that we can multiply to -2 so that we can get 1? Nothing. So, we cannot multiply any number from integer to get 1. Since we cannot think any number from the integer, therefore, there is nothing, or multiplicative inverse of integer does not exist. Since we did not satisfy the multiplicative inverse, therefore, it is not a field. It is just a ring. Let's have another example that has a that is a field. So let's have the Q. Yeah. Let's test if this is a field. Since in our previous lesson in group, it is an abelian, it is associative, and it holds a distributive. Therefore, it is a ring. Now, let's test if this ring is also a field. Let's get a number from rational so that let's try it if does have a multiplicative and additive inverse. So in multiplicative, let's try 1/2 times any number equals to 1. What number we can multiply to 1/2 so that we can get 1? We have 2. 2 is a rational number because 2 can be written as 2 over 1. 2 1/2 times 2 is equal to 1. Therefore, it is a multiplicative inverse. Next, let's try if it has an additive inverse. What we add to 1/2 so that we can get 0? It is negative 1/2. So 1/2 plus negative 1/2 is 0. Therefore, Q, the rational number under addition and multiplication, is a ring and also a field. That is our lesson for the day. The ring and the field.